Okay, so let's talk again. Let's complete what we've already seen on parameter-dependent integrals. All right, so what do we have in that case? We are talking about some function, let's call it big F of x, that is going to be defined as the integral of some function of two variables, f of x and t, and we integrate with respect to dt. First thing we want to know about is the continuity of that function. What does it mean to have a continuous function? It means that the limit as x tends to some value f x0 of my f of x should be equal to f of x0. And what is f of x0? It should just be the integral of f of at point x0 t dt. Okay, so that is still a question actually. So we need this theorem in order to answer, to be able to write this equality, right? And you see, it's again a problem of being able to exchange the limit and the integration signs, right? Limit of the integral is equal to the integral of f of x0 t is just the limit of f of x as x tends to x0. Okay, so it's really very close to the Lebesgue dominated convergence interval. Let's see what we need here. So we've got three hypotheses. Two of them are more or less easy to check, and the third one, if you remember, it concerns this dominating function. It's a bit harder to check, but let's have a look at this. All right, so maybe we should begin by this second hypothesis, which just tells you that you need that the function is continuous in x. Well, that seems reasonable because when we write this f of x0, we really mean the limit as x tends to x0 of f of xt, so that it can just be translated into an application of Lebesgue dominated convergence, right? So we need this to be, of course, equal to f of x0 t, and that means we need the inner function to be continuous, right? What else do we need? Let's have a look at that. We need that for fixed value of x, we can perform the integration with respect to t. Okay, so that's, but the thing is that if you can find the dominating function, this will be automatically checked because the dominating function is not supposed to depend on the x function, right? But that just means that, well, actually, you can perform this integral here has a sense. Okay, has a meaning. Okay, and then next hypothesis, and of course this is the important, the most maybe the most difficult one, tells you that you can find the dominating function that does not depend on x. Okay, why is that? It's in order to be able to apply again to Lebesgue dominated convergence theorem, and which the thing is, that's going to tell you that this integral here is actually doable, is finite, because you have been able to bound it whichever the x you are considering. So sometimes we have some problem to find the dominating function that is going to work for all x in I, okay, for all values of the x that belong to the interval where x has to belong to, okay? So we have a slightly less a constraining hypothesis to check. We just have to check it if that is true for any closed and bounded interval that is included in I. Okay, so we should have, we can give an illustration of that with the Euler gamma function. Okay, so let's switch to the study of, well, actually the first steps of the study of this function. Okay, that you remember, I asked you to work on that by yourselves. Okay, so let's have a look at this one. So Euler gamma function is this function that is defined. This is a nice parameter-dependent integral. Okay, and the first thing is first question that comes in that problem is about the domain of this function. Okay, so the domain of a function, you remember, it's just the set of all the values such that the function has a meaning. Okay, and it's not, it doesn't have forbidden values. So let's examine this for this function. All right, so we need to find for which x in R we have that the integral is converging. Okay, is well defined and converging. Okay, so let's see how we can prove that. Okay, so we have, so as you remember, we have an improper integral. So let's have a look at what's happening at the bounds. In between the bounds, let's assume that when t is not equal to 0, that's going to be well defined, and when t is not going to infinity, everything seems continuous and well defined, so we can use just the usual integral, and that's okay. So we study the improper integral. So in 0, what do we have when t is close to 0? Okay, so of course, be very clear about which variable you're considering. The integration is with respect to t, so that's the t that should be close to 0 or not. Okay, so what can we say when t is close to 0? When t is close to 0, e of negative t is, well, very close to 1, right? So my function, maybe we should give that a name, let's call that f of xt is the t x minus 1 e minus t. My function is going to be equivalent, f of xt is equivalent in neighborhood of 0 to t x minus 1. So we have to consider the convergence between 0 and whichever bound of t x minus 1 dt. And if you remember, that's exactly a Riemann integral. So what do we need? We need x minus 1 to be smaller than negative 1. To be bigger than negative 1. Okay, so that's the same thing as 1 over t1 minus x. And so if you remember, that gives you a convergent integral in the neighborhood of 0. If and only if I've got 1 minus x strictly smaller than 1, okay, which makes x strictly bigger than 0, right? So that's for the first side of my improper integral. We need x greater than 0, right? Let's have a look at in plus infinity. I mean t is close to infinity, right? Because that's what we are integrating with respect to. Okay, so in plus infinity, we can again use Riemann criteria. Maybe let's compare that to t squared. All right, so how do, well, or to 1 over t squared more precisely. So if I multiply by t squared my f of xt, that's going to be t squared times t x minus 1 times e minus t, which is equal to t x plus 1 e negative t, which is the same thing as t x plus 1 over e of t. What do we have as t tends to plus infinity as a limit? Well, tends to 0 by compared growth. Whatever the value of x, you know that if you compare the polynomial to the polynomial term to the exponential, it's going to go to 0, right? By compared growth. Okay, so what does that tell us? That tells us that f of xt is small o of 1 over t square, and 1 over t square is integrable in a neighborhood of infinity, so for any a strictly positive. Okay, so we can conclude that the integral is convergent and plus infinity for t close to plus infinity. So we have also gotten rid of the problem in plus infinity. All right? All right, so let's sum that up. That tells us that the domain of the gamma function is equal to r plus tau. Okay?